In the name of Almighty God, I'm Asa Sankoshi, and today I want to talk about the physics problems. This time, orbits. A particle of mass m is attached to one end of a spring, which a spring constant in a zero gravity environment. The other end of the spring is attached to a fixed pivot. The spring's equilibrium positions is fully compressed. The spring is stretched to a length r and the particle is given an initial angular momentum L. Which of the following is a possible value of r so that the spring stays at a constant extension r throughout the entire motion of the particle? After reviewing the orbits, I want to go to the next section 1.7 springs and harmonic oscillators. Spring problems appear in many different forms. True, they tend to use only a few basic facts. Obviously, Hooke's law is the starting point for the most problems when the F or Hooke's law is equal to is equal to minus chi x, where x is the displacement of the spring from equilibrium and chi is the spring constant. This is an ordinary differential equation describing a harmonic oscillator whose solutions are of the form xt is equal to r cosinus omega t plus phi. The angular frequency is given by omega is equal to square root of chi divided by m. Note that the amplitude r is not determined by the Hooke's law, but it is instead a constant of integration fixed by the initial conditions. The phase phi is the second constant of integration since complex exponentials is as equal xt is equal to r e to the power of I omega t, which are allowed to be complex, also satisfy Hooke's law, which is often easier to write the solutions in terms of complex numbers and take the real part at the end of the problem. This convenient shorthand will be elaborated in the chapter on waves, section 3.1.2. The potential energy of a spring constant core at displacement x is given by the u is equal to 1 divided by 2 pi x to the power of 2. You can prove this to yourself just by integrating the force from Hooke's law over the displacement of the spring to obtain the potential energy. In fact, this is all that you really need to know for solving spring problems. Like much of the rest of mechanics, spring problems at worst just reduce to solving second order ordinary differential equations. Simple as it sounds, this can sometimes be a time consuming task, so you should use the potential energy considerations whenever possible. To summarize, the order of operations for spring problems should be try limiting cases, dimensional arguments, and symmetry, try conservation of energy. The third one is try writing down a differential equation and solving it. Even this last method should not be too bad for problems on the GRE, but consider it as a last resort. Now I want to go to 1.7.1 normal modes. Now suppose that instead of having one body attached to a string, we have two bodies and we want to solve for the motion of both. This is complicated because we have a set of two cube differential equations with a large family of solutions. It turns out that all of the solutions, however, are just superpositions of two basic solutions called normal modes, which have the usual sinusoidal form of a harmonic oscillator. One very common GRE question is to ask for the normal modes of a system. The mathematical setup is as follows. Consider the general case of n masses attached to springs whose displacements are q car. Then the equations of motions for the entire system can be written as sigma, the lower boundary is car, or j car q car plus mj car q car is equal to 0. This is just the most general linear combination of coordinates that we can form out of acceleration terms and forces from Hooke's law. With great foresight, use the ansatz that is qt and the r Ka e to the power of I omega t. In this section, by displacement, we always mean displacement from the equilibrium. Whose from is inspired by 1.41 for the guess q car is equal to minus omega to the power of 2q car. So the equations of motion is reduced to sigma. The lower boundary is car rjk minus omega to the power of 2 mjk multiplied by alpha is equal to 0. This is just a matrix equation for the coefficients of alpha, and linear algebra teaches us that in order for it to have a non-trivial solution, the determinant must vanish. Determinant for the matrices rjk minus omega to the power of 2 mjk is equal to 0. This scalar equation defines a polynomial whose solutions give n frequencies omega I, which are called normal frequencies of the system. The normal modes alluded to above are just the solutions at which the entire system oscillates collectively at a fixed normal frequency, with the motion in time given by equation 1.42. A linear combination of solutions to an ordinary differential equation is still a solution, so we can build up more complicated motion by taking linear combinations of normal mode solutions with various coefficients. Often it is important to determine what kind of motion normal frequencies correspond to. For example, 1.12, we can immediately tell that the normal mode with frequency the square root k divided by m will correspond to the two blocks moving in synchronized with fixed separation. In this case, the middle spring has no effect on the system and the motion reduces to a single block spring system with total mass 2m and total spring constant 2k, thus giving omega is equal to square root 2k divided by 2m is equal to square root k divided by m. This should remind you of the discussion of blocks stuck together in section 1.3. We might guess that the other normal mode corresponds to motion of the blocks in exactly opposite directions. The frequency of this motion should be higher than the square root of k divided by m because the middle spring is now exerting an additional resulting force on the two blocks. Depending on answer choices given in the problem, these observations may be sufficient to pick the correct answer. Solving for the normal modes of a system is a very common problem in both quantitative and qualitative contexts. For a quantitative solution, the recipe is exactly as above. Write down the equations of motion for the system, then determine the matrices RJK and MJK, and write down the scalar equation 1.43 equation. Solve to find the normal frequencies omega I. In many cases, this machinery is overkill, especially as most GR problems are designed to be solved in about 1 minute. For most problems, you should ask yourself what are the simplest way that the system can oscillate at a fixed frequency. Drawing a picture is often helpful. Now I wanna go to the example 1.12. Two blocks of a mass m are coupled to each other and to two walls by springs of a spring constant k, as shown in the figure 1.15. What are the normal modes of the system? You see in the figure 1.15 illustrates two blocks and three springs with three different k. We start by writing the equations of motion. Let x1, x2 denote the displacement of the left and right blocks respectively. The force on the left block is the force due to each of the adjacent springs, giving an equation of motion mx1 is equal to minus kx minus kx1 minus x2. Similarly, for the right block, we have mx2 is equal to minus kx2 minus kx2 minus x1. Using our guess 1.42 for x1, x2, we find the equations of motion become m omega to the power of 2 r1 is equal to 2 car r1 minus car r2, and the next one is m omega to the power of 2 r2 is equal to 2 car r2 minus car r1. Writing this explicitly in matrix form, we have the first law is 2 car minus m omega to the power of 2 minus car. The elements for the second row is minus car, and the next element is 2 car minus m omega to the power of 2. Another matrix says I is I, R1 and R2 is equal to 0. Notice that we don't actually have to plug in the exponential guess solution to find this matrix equation. With practice, you can determine the matrices R, J, car and MJ car just by starting at the equation of motion for x1, x2 and jump straight to the circular equation 1.43. Taking the determinant of the matrix and setting to 0 gives 2 minus m omega to the power of 2 totally to the power of 2 minus cos to the power of 2 is equal to 0. Luckily, we don't even need the quadratic equation to solve this. Rearranging and taking the square roots gives 2 minus m omega to the power of 2 plus is equal to positive negative car. Handing us immediately the two solutions. Omega is equal to square root car divided by m square meter t car divided by m. What is the normal frequency corresponding to the entire system oscillating together? A general rule of thumb is a symmetric motion will have lower frequency than asymmetric motion, with the most symmetric mode corresponding to collective oscillations. In the case above of the blocks moving in synchronization having the lowest frequency, this is often the square root of car divided by m, where car and m are the effective spring constant and mass of the entire system, 2 car and 2m in the example above. Can this information be used to eliminate incorrect answers? And I want to go through the next subsection 1.7.2, damping, driving and resonance. What happens when there is an oscillator system with a damping force? One example would be a block spring system placed underwater where drag forces act to oppose the block's motion. As always in classical mechanics, our strategy is to write down the equations of motion of the system and find solutions. Damping terms such as drag or air resistance usually appears as a force proportional to the velocity of a particle. F damping is equal to minus Bx, so the general equation of motion for an oscillator which damping is mx plus bx plus cox is equal to 0 based on the equation 1.44. There are three qualitative types of solutions under damping: critically damped and overdamped. These are most conveniently expressed in terms of damping parameter. Beta is equal to b divided by 2m, and the neutral frequency omega 0 is equal to the square root of car divided by m. The underdamped solution for beta to the power of 2 is less than the omega 0 to the power of 2, corresponds to the motion in which the oscillations follow an exponentially decaying envelope. The equation of motion takes the convenient form xt is equal to re to the power of minus beta t cosinus omega 1 t minus delta, where omega 1 to the power of 2 is equal to omega 0 to the power of 2 minus beta to the power of 2. It's not critical to remember all of the constants in this expression, but it is valuable to remember that under damped oscillations are sinusoid with an exponentially decaying envelope. This should make intuitive sense. A small amount of damping which produce the same behavior as free oscillation, but with gradually decreasing energy and thus amplitude because of the damping force. The overdamped solution for beta to the power of 2 is greater than the omega 0 to the power of 2 corresponds to motion in which the damping is so strong that no oscillation occurs, while the solutions to the underdamped case are sinusoidal functions, for example, complex exponentials. The solutions to the overdamped oscillators are real exponentials, with the oscillator returning exponentially to its equilibrium position. The intermediate case between these two is called critical damping, and it corresponds to beta to the power of 2 is equal to omega 0 to the power of 2. A harmonic system can also be driven by some external sinusoidal force. In this case, the equation of motion picks up an additional term due to the driving. In the most general case, including possible damping, x plus 2 beta x plus omega 0 to the power of 2x is equal to all cosinus omega t. The solutions to this equation of motion can be found using elementary methods for solving inhomogeneous ordinary differential equations. Without going into details, the important point is that unlike the case of oscillator, which no driving force, the amplitude of the steady-state solution, that is after a long time has elapsed, is not a free parameter but instead depends on the coefficient r and the frequency omega of the driving force. For given r, amplitude is maximized when the driving force frequency equals the so-called resonance frequency. Based on the equation 1.45 is omega r is equal to square root for omega 0 to the power of 2 minus 2 beta to the power of 2. It is also possible to calculate the amplitude of oscillation when the driving frequency is different from resonance. It's extremely unlikely that you would ever need to the exact expressions for GRA, but it could be worth remembering the scaling relation in the absence of damping. The amplitude D of an undamped oscillator of natural frequency omega 0 subject to a driving force at frequency omega is proportional as follows. D is almost 1 divided by omega 0 to the power of 2 minus omega to the power of 2. Note that this expression diverges at driving frequency omega is equal to omega 0. Of course, we don't see infinite amplitude in real life oscillators because of small damping forces such as friction, but this proportionally should hold well near resonance in the weak damping limit. To summarize, we have three different types of motion with three different characteristics frequencies in order of increasing generality. The first is free oscillation. Omega to the power of 2 is equal to k divided by m. The next is damped oscillation. Overdamping, critical damping, underdamping, which characteristics frequency omega 1 to the power of 2 is equal to omega 0 to the power of 2 minus beta to the power of 2. Driving oscillation, omega r to the power of 2 is equal to omega 0 to the power of 2 minus 2 beta to the power of 2. Thank you so much for watching my physics tutorial video until the end. This time